Welcome to Study Time, a televised home learning program produced by Rwanda Education Board.
Hello everyone, I'm John, a math teacher. I'm back with senior 5 student in Unit 4, solving equation by numerical methods. Remember, we started by linear interpolation and linear extrapolation. After that, we tried to locate the root of a given function using the change of sign rule or graphical method, right? Now, this time, you're going to continue to solve such kind of equations. Somehow you can qualify them difficult equation, but not impossible to be solved. So we are going to try different methods, but for this time, we have a new method. The method is known as Newton-Raphson method, or known as method of tangent. But before that, let us have a simple exercise, this is activity. They're showing that 3x cubed plus x minus 5 equals 0 has a root between 1 and 2. And use linear interpolation to find the initial approximation of this root. Dear students, I give you 1 minute to find that root and to show that the root is lying between 1 and 2. Okay. Oh, fine. Hope you are done. Here you have the solution, right? We hope our function f of x to be 3x cubed plus x minus 5. And we have our interval from 1 up to 2. Remember that when f of a times f of b is negative, means that the function changed the sign, right? And of course, if it's continuous in that interval and change the sign, we have a root between that 1 and 2 in that interval, right? So our function is a polynomial function, and this kind of function is going to be continuous everywhere, of course, in the set of real numbers, isn't it? Okay. Now, for me, a is equal to 1, b equals 2. Then, f of 1 is equal to 3 times 1 cubed plus 1 minus 5. This is the 3 plus 1, 4. 4 minus 5 is equal to negative 1. f of 2 is 3 times 2 power 3 plus 2 minus 5. 2 power 3 is 8. This is 24. 24 plus 2, 26 minus 5, I get 21. Okay. So the product of f of 1 and f of 2 is equal to minus 1 times 21. This is minus 21, which is less than 0, is negative. Means that as the function is continuous in this interval and there is change of sign, therefore, there is a root between 1 and 2. So we're going to find the initial approximation to that root using linear interpolation. Then you can use this table. x and y. Of course, x or y is dependent variable, x is dependent variable. When x equals 1, we have the corresponding value of y is minus 1. And when x equals 2, the corresponding value of y is 21. Suppose alpha is my root. And as it is the root, it means f of alpha must equal to 0. So using linear interpolation, I'll be having 21 minus 1 divided by 2 minus 1 is equal to 0 minus negative 1 divided by alpha minus 1. This will be equal to, I hope this is 21. I'm sorry, it says there. I'll be having 21 plus 1, this is 22 divided by 1, which is equal to 1 over alpha minus 1. So by cross multiplication, I'll be having 22 times alpha minus 1, which is equal to 1. When I expand the left-hand side, I get 22 alpha minus 22, which is equal to 1. 22 alpha equals 1 plus 22 is 23. Means that alpha is equal to 23 divided by 22. Using your calculator, we get 1.045 to 3 decimal places. This is the initial approximation of that root using linear interpolation we did when we started that unit, isn't it? Now we are going to continue to find the approximation to this root using Newton-Raphson method, or known as method of tangent. How the method work? Okay. Let me have a function Newton-Raphson method. I need a function. I work in the Cartesian plane. You are following on chalkboard. X is independent variable, dependent variable. Let me have this function. This is y equals f of x. And let me take A and B at this level. And the function is continuous between A and B. Let me find the tangent at this point. This is x1, and there to be f of x1, and I have my tangent here. And my tangent is crossing the x-axis at x2. Let me have this root r, because the curve is crossing the x-axis, means the root is here. So if the root is here, and you have our interval, you see f of A is there, and f of B, if B is there, f of B is there, is positive, it means that f of A times f of B is less than 0, means that there is a root between A and B. So this tangent, let me call it L1. You know that the equation of that tangent is given by y minus f of x1, which is equal to, the gradient is f prime of x1 times x minus x1, isn't it? Here the point is x1 and the f of x1, the tangent at that point. Are we together? So when you observe this intersection between the tangent and the x-axis, I have the point, and that point is x0, no, it is x2 and 0, because any point lying on the x-axis, its y coordinate is 0. So when the point is lying on x-axis, also on this tangent, means that x2, 0, is lying on L1. Means that the coordinate of this point verify our equation, right? We are going to have replacing xy by 0, x by x2, I'll be having 0 minus f of x1, which is equal to f derivative of x1, then times x2 minus x1. Means that minus f of x1 divided by f derivative of x1 is equal to x2 minus x1. If I move x1 to the left-hand side, I'll be having minus x1 minus f of x2 divided by f derivative of x, this is x1, I'm sorry, of x1, which is equal to x2. Means that x2 is equal to x1 minus f of x1 divided by f derivative of x1. Are we together? So, and this is the approximation of the root. When x1 was close to R, means that x2 is very close to R, isn't it? Now, let me find another tangent at this point. X2, and of course, f of x2 is there. And the tangent, let me use this chalk. Let me call it L2, and it crosses the x-axis at x3, let me call it x3. If x1 was close to R, and x2 is very close to R, x3 is closer and closer to this root, isn't it? Of course, the equation of the tangent L2 is, of course, y minus f of x2, which is equal to the gradient f derivative of x2, x minus x2. And again, the point x3 and 0, x3 and 0 lies on my tangent, isn't it? So replacing y by 0 and x by x3, I will get 0 minus f of x2, which is equal to f derivative of x2 times x3 minus x2. And minus f of x2 divided by f derivative of x2 is equal to x3 minus x2. When I move x2 to the left-hand side, I'll be having x3, which is equal to x2 minus f derivative of x2, f of x2 divided by f derivative of x2. Are we together? Oh, very nice. I'm going to continue using another line, but when I'm preparing the chalkboard, you can take your time to write something in your notebook. Okay, we are back. If we try another tangent, probably at this point, this is f of x3. The tangent is looks like this one, right? And this is x4. You realize that x4 is very, very, very close to this root. As we make many tangents, we are approaching the root. Means that using the same method, the equation for L4 and solving for x4, we shall have x4, which is equal to x3 minus f of x3 divided by f derivative of x3. Is it difficult? Not at all. It is very simple and clear. Similarly, if we continue with another tangent, we shall have x5, which is equal to x4 minus f of x4 divided by f derivative of x4, like this. It means as we make a big number of tangents, means that n is approaching to infinity, okay? I'll be having xn plus 1, which is equal to xn minus f of xn divided by f derivative of xn. And this is known as the Newton-Raphson formula. But pay attention. I can fix x1, but when I try to find x2, I get a worse answer. Means that the method fails, and I have to consider my x1 as the approximation of that root. That can happen when this derivative is very, very close to 0, or simply this derivative is equal to 0. So it means when it is equal to 0, the method fails. We can find other way of approximating that root. Okay? I hope you have understood the way we are doing that. And when xn is moving from n to n plus 1, those are iterative values. Iterative values. And as xn approaching to this root, means that the sequence of xn plus 1, which is equal to xn minus f of xn divided by f derivative of xn, is converging to our root r, isn't it? It can happen, maybe x3 or x4 is out of my interval a and b. When it is out of that interval, means that my sequence is diverging. And, of course, the method fails. We have to look at another way. There are very many, but this moment, we are going to stop at this method. You may need an example. I was trying to explain the way. So example, use Newton-Raphson method to find the next two approximation to the root of the equation x cubed plus x minus 1 equals 0 using x naught equals 0.5 as the initial approximation. It is very simple. Example is still there, but I'm going to give the solution. We have f of x, which is equal to x cubed plus x minus 1. And the initial approximation is x naught equals 0.5, okay? Then we need the derivative of this function, which is equal to 3x squared plus 1. Using this formula, xn plus 1 is equal to xn minus f of xn divided by f derivative of xn. For me, if xn, x naught equals 0.5, it means n equals 0. Means that the next approximation will replace n by 0, and you get x1, which is equal to x naught minus f of x naught divided by f derivative of x naught, right? And you get 0.5 minus f of 0.5 divided by f derivative of 0.5 means that you replace in this function x by 0.5 and in this one by 0.5. You have your calculation in your calculator. The answer is 0.71428. This is x1. We need find the next two approximation. Means we are going to find also x2. x2 is x1 minus f of x1 over f derivative of x1, right? It means that I'll be having x2, which is equal to 0.711428 minus f of 0.71428 divided by f derivative of 0.71428. You have your calculators. After calculation, you'll be having 0.68318. 0.68318. This is the third approximation using, of course, Newton-Raphson method. Remember, when we are approximating the root, we shall make errors. So how will you know if you have to stop? In case you get xn plus 1 minus xn, which is equal to the given error or tolerance limit, tolerance limit. So you have to stop. Okay? So you follow the result for that example, right? And here you have another example to you, but of course, it is like auto-evaluation. I'm not going to solve that. You are going to follow the method used, and you do it yourself. Starting with x1 equals to, find the third approximation, x3, to the root of that equation with a possible error of 0.05, correct 4 decimal places. Of course, the answer is there, but you are going to find it. Okay. When you are done, you may have a homework. The homework is no different from what we did here. We have our equations. Normally, cubic equations are not easy to solve, but when you try to graph them using maybe derivative and whatever, you can find the intersection, and you can approximate that intersection, which is the root, by different methods we solved. Then use Newton method with given initial approximation, x1, to find x2. Sorry, this is x3. The third approximation to the root of a given equation. Give your answer to 4 decimal places. 1 is x cubed plus x plus 1 equals 0. The x1, you're going to use minus 1. Number 2, x cubed plus x plus 2 equals 0. Take x1 as minus 2. That is the first approximation. 3, x power 5 minus 10 equals 0. Take 1.5 as the first approximation, and so on. And the last is x cubed plus x squared plus s minus 2 equals 0. In this interval, 0 up to 1, when this approximation, the initial approximation is not given, you will take 0 plus 1 divided by 2, the middle, right? 0 plus 1 divided by 2, and you get 0.5. Take 0.5 as initial approximation. Hope you have understood my lesson. It was interesting. I'm very sure it will be helping for solving different equations. Thank you for your attention. Thank you for your participation. I hope to meet you next time. I wish you all the best.